development engineer here at Consteel, and I'm really excited to show you and to present our newly developed tool called FALCON. And in the next 1 hour, 1.5 hours, I would like to briefly introduce what this new tool is about. So let's begin. I would like to start by diving into the topics. To begin, I would like to share some introductory insights about our newly developed tool called FALCON and its theoretical foundation, introducing a few thoughts regarding CFD and how it is integrating in structural engineering. In the second part, I will focus on simulations themselves, particularly the post-processing steps, which we consider as a distinctive approach. This will be followed by a demo in Consteel, concluding with our vision for how our valued community can actively contribute during this beta phase. So, in this first slide, my aim was to encapsulate everything about FALCON in one picture and with a few sentences, highlighting its place within our software ecosystem. FALCON, our fluid dynamics aided loads in Consteel plugin, is a universal load generation tool supported by fluid dynamics simulation. Its initial release is exclusively integrated and works only with Consteel version 18, and it is designed to empower structural engineers to accurately determine wind loads for any building type comparable with standard guidelines. Key point is that FALCON operates as a standalone solution, yet it remains closely tied to Consteel's workflow for seamless integration into the existing load evaluation process, which uses specific surfaces, so-called wind simulation surfaces, and a few parameters like velocity pressure parameters, internal, and several geometric parameters. This is further enhanced through dedicated dialogues for simulation settings, providing a calculation or a computational engine or an algorithm that tries to mirror the standards while reducing and eliminating the limitations. FALCON aligns with engineers' wind load assessment methods, offering greater flexibility for users to incorporate their expertise during post-processing, particularly when we'd like to try to extrapolate precise wind loads from simulations. In the future, FALCON will be integrated in other solutions, our solutions such as SteelSpace, for instance, to exploit the strengths of cloud services, and also in Pangolin to offer integration in parametric design workflows. So let's continue with a few preliminary thoughts about the background of this development. Today's webinar focuses on presenting a new function rather than diving deeply into fluid dynamics. However, given the complexity and the vast amount of knowledge we've gathered over the past few years, it's challenging to condense and share it all in such a short time. So for this reason, we plan to provide detailed trainings to offer a more comprehensive and responsible understanding by the end of this beta phase. Of course, if you have any questions, please feel free to ask in the chat and we'll address them as quickly as possible. But speaking of questions, the main one might be, can we accurately capture how the wind flows around the building? This is obviously it's a complex question, and there are at least 17 problems with this on this picture, as you can see, because the air has several tendencies, how it flows over the building, how it separates at the sides, creating vortices and eddies behind the building. So instead of directly answering these questions, let me pose a follow-up question. Is understanding the flow streamlines around the building is really what we need? Because our primary focus is on the pressure fields rather than the velocity fields. And it is more importantly, how to convert or translate those pressures into quasi-static structural wind loads to use for actual design. But how these fields, these pressure and velocity are related? Well, CFD seeks to solve the continuity and Navier-Stokes equations, in which the turbulent Reynolds stresses are required to be known beforehand. So meaning you need to know a part of the answer before you actually can solve the equations. This is called a closure problem, and the different CFD methods address this in different ways, which balances computational effort against accuracy. Therefore, to efficiently deal with simulations, we are trying to mathematically model several terms. For instance, this Reynolds tensor, which models viscosity and requires an initial estimation or boundary condition at the inlet side of our simulation domain. Another simplification that we seek for a steady solution. So instead of unsteady Reynolds averaged Navier-Stokes equations, we neglect these time-dependent terms. So this will result quasi-static structural loads. Now back to the different CFD methods. Here you can see a quick summary and comparison. For industrial purposes, the most common are these runs or Reynolds averaged Navier-Stokes equations, which using different turbulence models, for instance, the simplest is K epsilon. These are trying to mimic a simplified air motion. And this would be probably the most efficient way to calculate. However, the most complex one and the most realistic one is the direct numerical simulation, which resolves the entire range of turbulence scales. And it is intractable for the complex flows around the building. So it's really hard to, or almost impossible to calculate with current technology. But the best compromise is probably the large eddy simulations, which are compute the turbulent eddies down to a threshold size, below which this Reynolds averaged Navier-Stokes is used. But again, the question remains the same. Do we have to know all the streamlines and the accurate motion around the building? Because as you can see here at the left side, a result from the simplest Reynolds average Navier-Stokes method. And at the right side, we have this large eddy, which captures these larger vortices and it mimics the more realistic behavior of the airflow around the building. But again, for us, it is much more important to capture the pressure fields on the buildings. So at the end of the day, no matter the computational methods, the reality is that the most efficient solution wins, because we have to make the most out of these solutions. So how we can effectively execute these kind of solutions or simulations? Well, we are not the only ones who integrated OpenFOAM as a CFD engine, which itself is a C++ library without general user interface and without any structural engineering context. Therefore, for industrial purposes or for day-to-day simple use, it is not an efficient solution. However, it is really powerful. It has a lot of powerful solvers and has different tools to efficiently pre- and post-process the data for solving simulation cases. And speaking of pre-processing, I would like to highlight one specific utility of OpenFOAM that makes a key difference between the world of mechanical finite element analysis that we are used to and computational fluid dynamics, and this would be mesh generation. For every simulation case and for every building, therefore, and for every direction within a finite domain, the building needs to be introduced in this computational setup. Following this, the mesh must be refined to create a negative imprint of the building, and these steps are essential to accurately compute the pressure and velocity fields within these cells to a required level of precision. And how does this mesh refinement process looks like? So first of all, if we have now in 2D only, but if we have a simulation surfaces, which is bounded by a few edges, we have to introduce this in our domain, which is already discretized. So we have a few blocks inside our domain. After that, we have to refine this domain according to the edges of our structure. And according to this refinement, we have to get this negative imprint of our building, or in this case, simple car. But the idea is that we will have a zone or a computational domain or a portion of this domain which is much more influential, where the results are really influencing the pressure fields on our structure. Therefore, these zones has to be refined. And what this refinement means, that we have a basic block dimension, let's say at the inlet side of our simulation domain. Let's say it is 8 meters. And with every refinement step, these cells are divided by 2 actually in space. So from a block of 8 by 8 by 8 will be a few 4 by 4 by 4 cells, and so on, until we get a precise mesh size on our structure. So this is a really important step if we'd like to understand how FALCON in the background is working during these meshing processes. So this was all about the, let's say, the theoretical background of CFD. But again, we are really focusing on during our trainings, which we are just started to develop. So we will be really focusing on these theoretical backgrounds. But now I would like to highlight or to try to harmonize the CFD world with our structural engineering mindset. So let's dive into a few topics and actually just repeat a few basic assumptions that we are all familiar with. When it comes to wind loads, the standards are usually assuming an atmospheric boundary layer where the wind consists of 2 parts actually. The one is a stagnant mean velocity term, which is VM from the standard, and the other, and it is defined according to a terrain category from that table from the Eurocode. Then this mean velocity is multiplied with a turbulent term, which is enveloping the fluctuating behavior of the wind, which is obviously this time dependent fluctuation. And its intensity is also influenced by the terrain category. However, when it comes to turbulence, it is important to differentiate 2 things or 2 behaviors. One is that turbulence is modeling the natural behavior of wind, or during turbulence, when we call or talking about turbulence, the natural behavior of the wind is one part of the equation, because when we have a finite domain where the wind is inserted, or we have an inlet side where the wind is coming towards our building, we already can take into consideration this turbulence term based on the obstacles or caused by the obstacles or the actual terrain category. So this is already a peak wind velocity, which we introduce in our finite domain, containing the turbulence caused by the neighboring buildings. However, the turbulence occurring around the building is causing different pressure and suction zones, and these are taken into account in the form of pressure coefficients. So these coefficients then are multiplied with the peak wind pressure. And this is how we reach the actual pressure loads on the surfaces. So this is the methodology of the Eurocode, which we all know. But the reality can often be quite challenging or confusing, at least, because in most scenarios, we lack precise solutions tailored to specific building types. And this is one with an engineering approach, we try to apply general solutions to unique situations. Naturally, this approach raises numerous questions and uncertainties along the way. So the solutions of the Eurocode is not for any type of building. However, these are precisely the kinds of questions that the second generation of the Eurocode aims to address through more detailed setups, because currently it is in the publication phase. This updated standard and introduces several changes and clarifications. So I really encourage you to compare the existing version and this new draft to see the differences. But while the revised Eurocode offers more sophisticated solutions, for example, the approach on the left for non-rectangular planar buildings, or the one on the right for non-uniform height buildings, many questions still remain unanswered. For instance, what happens when we encounter a building that is both non-rectangular in plan and has non-uniform height, a situation that occurs quite frequently. So can simulations provide reliable solutions for such scenarios? Because Eurocode probably will never be a standard which contain for every possible scenario a direct solution without any uncertainty. So probably simulations with time have to be, or in our opinion, should be even more used to exploit the possibilities in CFD, also in our domain. But as responsible engineers and developers, we want to be really transparent about the limitations, because for detailed design, the direct use of computational wind engineering, this CVW, just to highlight that. So for detailed design, this direct use of computational wind engineering or molecular simulations is not advised. However, wind tunnel testing remains the preferred approach, also for preliminary stage and for detailed design. And here I would like to emphasize the importance of this direct use of these simulation methods, because this is where we see the value in incorporating this post-processing phase, what we call. By using simulation results in a manner similar to the Eurocode, applying more conservative loads to specific zones, and offering the flexibility to override these results within certain limit values for suction, for pressure, and so on. So we can achieve a safer design approach. This method strikes a balance between precision and reliability, obviously, but it also requires thorough validation during this beta phase. And based on these results, what we have up until this point, we really believe in this direction. So now I would like to focus on the actual workflows and how the simulations are working in our environment. But I would like to start with what were the first steps during this development? Because when we started this a few years ago, we realized that there are several parameters that actually can be narrowed or fixed, because only for structural engineering purposes, a lot of simulation parameters can be the same, like how we consider the inlet of our calculation domain, because we will always have such in a, or also like in a wind tunnel, we always has a inlet side, we have an outlet side, we have a ground, where we can where we have several assumptions regarding the wall functions and how the actual pressure distributions and velocity distributions are forming. So there are several parameters that can be, for structure engineering purposes again, can be fixed. And here you can see a diagram regarding how the distribution of different parameters. And you can see that actually the mesh generation, the creation of the simulation mesh is the largest part of this process. And obviously the second most important thing is the solution. And only a small portion is that how we introduce the wind flow and how we incorporate the standard logic or the standard wind profiles from the Eurocode. So for these larger parameter set, how we reached this narrowed user interface or this narrowed setup of these simulations, we have two knowledge-based materials already. And these are only focusing actually this pre-phase of the simulations when we are running the actual or when we are executing the simulations. So from up until this point, we only publish these two just to understand what are the basic assumptions behind the calculations and how the different parameters are influencing the actual simulation results. So I really recommend to read about these topics, but I also like to mention that from now on, we would like to focus on this post-processing phase, because when we launch the FALCON, you also will be able to compare with us together these results and to start this community development, what I will talk about at the end of the presentation. So again, we did our part regarding this research, and I would like to highlight a few things about these major steps, because I already used these terms pre-process, data process, and post-process. So pre-process is what we call the process when we are creating or converting our geometry to a specific mesh. I will talk about this later. What does it mean? And we create this virtual wind tunnel with its wind profile according to Eurocode, with its boundaries and a few blocks, a discretized domain where we are introducing our building. So this is the simulation case. However, it is already taking into consideration these two softwares that we are using. Consteel, which has its own dialogues to define these meteorological effects. So this would be the wind profile part. And we are also taking into consideration OpenFOAM, and we are creating and translating all this information to this specific format for OpenFOAM to run a specific simulation. But I also will show you a bit later what does this mean. Okay, regarding the wind profiles, just really quickly, because you can reach about this in our knowledge base materials. Just one thing I would like to highlight is that in the standards, we have this QP Eurocode profile, let's say, with this orange one, which we would like to also mimic at the windward side of the building. We'd like to reach the same pressure values on the windward side, because those are those are exact pressure values, so positive pressure. But to reach this, we need a velocity profile, which can produce this specific peak pressure profile. So this would be this velocity inlet, this orange profile, which I showed in a comparison with other profiles of the exact Eurocode, the peak velocity, and the mean profile from the Eurocode, also the atmospheric boundary layer, which is the basic open foam profile. What I would like to highlight here is that neither the open foam basic profile is not suitable, but also the Eurocode wind calculation method is not exactly producing those pressure values that we are waiting for. Therefore, it was needed to introduce our exact wind profile, which you can read about in our knowledge base materials. So again, this was the wind profile part of the pre-processing stage. But what about the mesh generation part? Because here I would like to highlight that there are two different meshes. The so-called finite element mesh, which is I also call our mesh, which is an offset mesh, because this was specially developed for finite element purposes, which means that this is a specific mesh that contains only planar faces. Therefore, it is suitable for load creation, for mechanical structural loads creation in Consteel. It is also suitable for zoning because as I said, it is an offset mesh because it takes the edges of a simulation surface and according to a mesh size, it tries to, by offsetting, it tries to create cells. And therefore, at the edges, we will have this smooth quad mesh, which can result better zoning, a better mesh for zoning purposes. But you will see understand this when we have results. But in the other hand, the finite volume mesh of open foam is a specific mesh, which is an angle, which contains anagon faces, which means can be a face with 8 vertices, for example. It is really important that it can be distorted, meaning that when you introduce this building in this finite domain, during this mesh process, the building or the cells around the building will be iteratively distorted to reach this negative calculation domain. Therefore, it is not always planar, so it is not always suitable for load creation in the Consteel. This means that we have our results in this mesh offered by OpenFoam, which we project to our mesh, which is suitable for post-processing and for load creation, which is comparable to Eurocode. Another aspect is that our mesh is independent from wind direction. You will see the same faces for every direction, while the open foam mesh, this finite volume mesh, which contains volumetric cells in a domain, is dependent from wind direction. So for every case, for every simulation case, for every direction, will be generated a separate mesh to capture the velocity and pressure fields around and on the building surfaces. Okay, so having all this in mind, how we can offer parameters for FALCON and therefore for OpenFoam. Another really important aspect is the geometry itself, because when we are talking about a building or a simulation for a building, it is really important to decide actually the level of accuracy, what it is important for us, what we are designing actually. Because for instance, for this scenario, which is not typical Consteel building, but it has this, let's say I call this the standard dish case, because it is containing vertical walls. Okay, it has different heights, and in plan it has different it has a specific angle between these walls, but it can be approximate, or we can approximate realistic values on it, but we always have this uncertainty because the standard does not tell exact solution for this type of building. And if, let's say, we have for this building, we have a secondary structure behind, let's say, some trapezoidal sheeting or some kind of sheeting, and we like to design those members, we can create a simplified model of this building, which does not contain every element of the balcony and every the entrance. It is a simplified model of the building. It is a simplified, closed, solid of the building. But obviously, it has its surfaces with where we would like to have results, and the rest of it is these are just obstacles. Like in this scenario, which is a even more specific case where standards are way out of what an engineer actually would like to know, but it is a situation where we have to introduce some obstacles, some nearby buildings, because we would like to, in this scenario, design this free-form structure above this building. So we have these two situations, which are, let's say, the first one is quite a normal building, while the other one is a specific case. But they have one thing in common, that they can form a closed building or a closed solid, which we can introduce into a calculation domain, and we can obtain simulation surface loads, which will always be surface loads. But what about beam elements and beam type structures, like let's say a high intensity voltage tower, or any type of tower type structure, or in this scenario, just a simple structure without any sheeting? Can we use simulations? Well, my response is that we can. However, we don't recommend, because it is not a efficient way of using simulations, because it really needs to have a correct envelope or a correct mesh around these buildings. So we have to use a specific so-called shrink-wrapped mesh. So we have to wrap all this structure into a closed. At the end of the day, it has to be a closed solid, because again, OpenFOAM and CFD in general, because it is a 3D, it is a spatial calculation, it always requires a finite volume mesh. Therefore, if we have these member type structures, we always have to make sure that this is wrapped and it is suitable for load creation. But again, it is not a too efficient way of calculation, because it is really hard to decide how the different pressures are acting actually on a beam member. Therefore, in this beta phase, FALCON is recommended to use for surface geometries. Because what are our experiences regarding using these type of beam member structures and other, let's say, landmark type structures? This is what I would like to talk about just quickly, because we tried to reach the limits of this tool or these simulation methods, these simplified Reynolds average Navier-Stokes based approaches, which again are capturing the main, and they are just only modeling the main vortices around the building. Therefore, for example, if we have this type of landmark structure, a stadium, which again I try to, if you see this section, I try to enclose this below the stands. It is so the building actually it is closed, it is wrapped. So I try to run a simulation on this, and I get results which is kind of boring, to be honest, because this is what we expect. We have a pressure at the windward side. We have some pressures at the closest edges. We have a higher suction values. But what happens at the end of the structure, or if we are curious about this region where can form these vertices, these where the situation is much more complex, because we have the interior of the stadium where the air can move. So what happens in this scenario? Well, the answer is that with these turbulence models, we don't know exactly. We will have this constant value, which is already the pressure distribution is already quite low in this zone. So where actually matters at the end of this console type truss roof, at the end of this where we are really curious what are the forces, the acting forces from wind, we cannot predict accurately. Therefore, for these scenarios where the building is too complex and we cannot capture, and we are really interested in the inner or in the inner behavior of the structure, or for structures which are beam type structures, where again the result is quite let's say boring, because we only have constant values here. We cannot exactly capture what happens below the structure, where probably turbulence is way much or way more interesting, or way more important. So we don't know exactly. So these are our experiences, and I would just like to share this with you, how we can see in this beta phase what type of structure are suitable. So again, those first two structures that I showed you can be, for those two can be used these methods. But I will show you immediately those results in Consteel directly, because the next step would be post-processing simulation. Just quickly, a few words about what happens when we are talking about this. As I said, we have our finite element mesh, this so-called offset mesh, where we have these quad faces, and in every phase there is a result projected from the open-form mesh. So this is, let's say, the direct approach, or the direct use of a simulation. But if we'd like to post-process these results, we try to reach several zones where we have larger surface loads, which are already trying to mimic this zoning procedure of the Eurocode. Therefore, they will be comparable with the Eurocode, because we will obtain larger, obviously much more conservative loads, but based on the simulation results. So it can be used for almost any type of building. And This type of post-processed results can be then later manipulated with different limits and can be compared to Eurocode directly, or obviously for the situations that we know, we can validate this. And this would be this beta phase that we are also waiting for your interesting models and for your help. So again, this would be in a really boring structure in this cube, this post process where we are trying to reach a conservative surface loads on the structure. But how does the actual workflow looks like? And from now on, I would like to change to Consteel. So let's see the actual procedure. I just go to my model. So here we have, okay, so here we have, again, a really boring structure, I know, but this is a, let's say, the simplest case where we can already capture different values which we can compare because it is a basic structure type from Eurocode. So we can conclude a few things. And also it is quite small, so I can run a simulation live with you together. So let's see the procedure. So the first steps were that I just modeled the contour of the structure, let's say. So I have a few columns and beams and surfaces which are in Consteel's user interface. These are load transfer surfaces. So this is our structure actually, which is, again, it is a sealed structure. It is closed. Therefore, we can reach this negative in the simulation domain, and this is the where we are starting. So where we can find FALCON and how we can use it. So at the load step, we have 5 icons which are related to meteorological load generation. You are probably also familiar with the first 2, which were actually only 1 icon in the previous versions, which is called meteorological effects, where we defined the velocity pressure. So let's do it, which depends on the terrain category. We have to define a basic wind velocity based on our local standard-based values to obtain this velocity pressure profile. Okay, so this would be the velocity pressure parameter set. After that, we can, but it's not a must to define internal pressures, which are actually also for simulations. These are only values that we are adding or subtracting from the simulation. These are results to mimic the effect of a internal flow behavior. For this example, I won't define any internal pressures, and let's see what kind of geometric parameters we have to define in Consteel. The most important one is the main direction of the simulation according to the global coordinate system, which is in this scenario the positive x direction, meaning that the positive x direction will be the 0 degree from the wind point of view, so from where the wind is coming. Other parameters regarding the building dimensions, these are similar, and because we really try to integrate to the this Eurocode methodology, we also use these values for simulations just to recommend some starting values for meshing processes. For example, in the Eurocode, you have to define the parallel and the perpendicular dimension of the structure, which is obviously not a straightforward dimension, but it is really depend on what we are designing. Because if we have a structure with non-uniform heights and we have a tower, let's say, at the end of the structure, so we have different heights. If we are designing that exact tower, then we should write here the building dimensions or the dimensions of the tower. If we are designing the whole structure, we should take into consideration the bonding dimensions of the structure. But again, these are only used to recommend a certain meshing value, which I will show you immediately. After that, we have this loaded area, which we are not using for any. So we are not using for the simulation. And we have this ground level. According to the Z axis, you can define a certain height where you consider that there is the ground of the simulation domain. So here we have our geometric parameters. And this was the definition of the meteorological effects. Let's go on. How we define these meteorological surfaces, or how we can tell to Consteel which surfaces we consider as a surface where we would like to calculate simulation results. The walls of the structure, the roof of the structure, obviously, inner surfaces, inner levels of the structure should not be simulation surfaces, but actually it is a similar method or a similar method how you can define wind surfaces with our previous meteorological load generator tool. So again, we had this wind surface previously, and now we have this simulation surface. So first of all, I just choose this simulation surface, where again I can choose how that specific surface will be taken into consideration. The general means that it is a simulation surface where we will get results. The obstacle is just simply a surface which will be taken into consideration, but there will be no loads or no results saved on that specific surface. Therefore, we cannot generate loads there. So again, we have these simulation surfaces, and that I just quickly define for all of my surfaces. And just to compare later the results, I also define wind surfaces for the walls, for all the 4 walls. And because in the Eurocode we have this dual pitched roof, I also define wind surface. Again, you can check these. This is the icon for simulation surfaces, and this is for the standard wind surface icon. So this was the process, which is really similar to what already been in Consteel. And before creating any simulation loads, just to play with your patience, I will first generate loads based on the Eurocode. This is also a tool which has existed in Consteel. So for the 0 and 90 degree direction, I will generate only wind loads without an internal pressure and wind friction. So let's see the results. So we have these 2 scenarios from 90, and because the angle of the roof is around 25 degrees, it is a scenario where we also have pressure and suction values on the roof. So this was the generation according to the Eurocode. And here it comes the interesting part. how FALCON works in Consteel. So this is the dialog of FALCON, which when it is opened, it is already checking what is in the model. Again, it is a standalone tool. So when you open this, you can, when any type of simulation is running in the background, you can use Consteel. Again, it is not very recommended to run analysis and change. The main thing here is to change the model, because the simulation is running on the actual geometry, and in the meantime, if you change anything, obviously it won't be taken into consideration. But again, it is a standalone dialog where you can define after the effects and the surfaces, which, as you can see here, are checked. So we have 6 simulation surfaces. We can go on. You have to we have to define the simulation settings. Here we have the basic settings, because we try to really simplify the dialog to those parameters which are really matter. The first one, and probably the most important one, is the mesh size on the structure. And in this scenario, it is 600 millimeters. This was calculated or proposed by FALCON, knowing by the given those parallel and perpendicular dimensions that we defined previously. This is there is nothing sophisticated, so it's nothing complicated in the background. These are trying to mimic that E value from the Eurocode, which you are probably familiar with, which defines the dimensions of specific zones. For example, at the roofs, you have E divided by 10, and you can define the width of a specific zone, like here. So this 600 is probably because we have a 6-meter building, or I don't know exactly, but it is calculated according to the dimension of the structure. But obviously we can change, and it is recommended when you are at the beginning, because simulations are, or simulation in general, or CFD in general, I really think as a iterative process, because the results that we can obtain can be really fast if we have a large mesh and a small domain, and it is quite easy to calculate. But obviously, the precision of the values is questionable. So, but again, to have a valid geometry and valid setup, it is recommended to run a simulation with higher values, meaning with higher mesh sizes and higher refinement values. This refinement factor is that what I was trying to explain at the beginning with the refinement of the structure when we introduce a structure in the domain. So we divided 2 times, we divided the basic block, if we use the value 2, or we can use 4, meaning that we have a mesh size on the structure, and it is 4 times bigger, the block at the inlet side. Okay, we have a lot of explanations here, because sorry for it is quite hard to explain in a few minutes the usage of these parameters and how all this dialog works. But we tried to simplify this with these tooltips, where you can read about the parameters. We also have the manual. I will show you at the end of the presentation. But again, you can always check the meanings behind these using our tooltips. So we have these basic mesh sizes, and we have also this tick where we can set if we actually want mesh, but not on the finite volume mesh, which is for the open form, because it always will be meshed. But let's say if we have a structure where we have which is pre-meshed, like a free-form structure, where every roof element is already considered mesh, there is no reason to have these zones, because for every portion or for every roof element, we'll have a separate value. I will show you an example on another model. Just a second to find that model, because I have multiple opened. So here we have, this is a scenario what I already shown to you during the presentation for a structure which consists of around 1000 surface elements, and it was performed simulations in 2 directions, from this side for 180 and from this side from 90 degrees. Here you can see that we have quite a few so values that we are expecting, for example, at the windward side, because here we have an inner zone where we have smaller pressure values. We have this load intensity of 0.2, while here we have almost double. So because we have this inner zone, the values are lower. Again, which is probably much more important, that we have suction values only in this roof, but sorry, not only suction values, because where we have a nearby roof at the edges, we have a few pressure values. So we have a more realistic pressure distribution on this structure. But again, having these results, I can anytime trying to understand using my structural engineering knowledge base, which probably based on standards, it is known that if you have a domic or spheric structure, you have these suction values where you have a value, which is smaller, while you have a B value, which is the highest one at the middle, and we have a C value at the end again, which is at the leeward side. So you can easily compare results from simulation. Again, this is a scenario which contains multiple elements, which does not require additional meshing. So this is when for one simulation surface, there is only one surface wind load. So in this scenario, that tick has not to be active, that flag with the meshing. Okay, so another thing regarding the structure is that when we have a closed building, it is always important to know which is the inner and which is the outer side of the building, which is obviously sounds quite straightforward, but from a modeling point of view, it is not always taken into consideration, because when we are drawing simulation surface, or in general, we are drawing load transfer surfaces, we are not always taking into consideration the local axis of these elements. But to have correct loads, it is really important, because as our generator, our Eurocode generator works, this is how the FALCON works. So if the simulation surface local coordinate system is pointing outwards, it means that if we have a suction value, or if we have a negative value, it will be a suction on the building. Because from the simulation results, we know only that we have a positive or negative value. But if we have a negative value on a wall, it is not straightforward in which direction is applied, or the suction is applied. Therefore, when you are running simulations, you always have to take care that all the coordinate, or all the local coordinate system has to point outwards from the structure. For this, we are when you are running simulations, we have a few checks which which are regarding if the building is sealed, because we are verifying if the building is sealed, meaning that the corner vertices are connected and the building is closed. However, you have to be ensure that the directions of these local coordinates are appropriate or adequate for load creation, which you can do by setting local coordinate system. This is just a parenthesis that I would like to show you, because we have this tool that meaning set user coordinate system z-axis by a point, meaning you just have to select the obviously we are working with surfaces, so you select the surfaces and you just have to point an inner point in the building, and all the surfaces will be pointing outwards. So it is really convenient, but you have to make sure that your building is modeled adequately. So this was actually the second example what I show you in the presentation. So let's go back to our live demo. So as I said, we have this these basic simulation settings, but obviously we have a few advanced ones, which are, for instance, the turbulence models, those one which we are already implemented, the most common ones, K epsilon and K omega. I really recommend to read about these, which are suitable for in our industry, but it is not so straightforward. But in every other solution, the key epsilon or every other software solutions for CFD in structural engineering, the key epsilon, the key omega, these are the most common ones. So I recommend these ones. These are which we implemented. You also can define the number of processors, which can be obviously the highest value is the threads of your processors, but here is really important to mention that we set as a basic or a default value 1, because it is not always the case that using most processors leading to faster simulations, because when we are running in parallel, or we are executing simulations in parallel, both for meshing and for simulations, we have to decompose the simulation domain, meaning we just simply have to cut in. If we have 4 processors, we have to cut, or not we, the software will cut in 4 finite domains, and every processor will have its own domain where the calculation will be performed. But at the end, you have to the software have to reconstruct the results, meaning there is a decomposition and the reconstructing phase, which takes time. So it is not always a straightforward method to use all of my processors, because if I have a simple structure, probably with only using one processor, the result can be obtained faster. Okay, you can define the number of iterations, which means if you don't have convergence, which in this scenario is a value, which means the difference between 2 iterations for all the fields, meaning you have 2 iterations, and in those 2 you have pressure, 2 specific pressure or velocity values, and if the difference is smaller than this convergence criteria, the result is considered converged. Therefore, the number of iterations will be not reached. In any way, we are monitoring this during the simulation, which I will show you immediately. And if you haven't reached the convergence, you should probably use more iterations to have an adequate result. Obviously, these are the simulation parameters which are influencing the execution of OpenFlow. In the beta phase, we try to simplify these parameters. Again, we just narrowed the number of parameters with these ones, which does not mean that at the end of when we publish the commercial version will be simpler, but maybe it will be even more complicated. We don't know yet, but this is just for the beta phase. So these are the simulation parameters for OpenFlow, and these are the domain dimensions parameters, which we also consider as an advanced setting, because this is based on experience, literature. This has to be a value or values actually, because these are multipliers according to the height of the structure. We have to define the windward side, or how long has to be the portion of the calculation domain behind the building, near the building, to form this calculation domain. So we have these multipliers. I think the picture is quite suggestive, so you can understand easily how you can change the value. But again, these are some default values according to literature, which can be changed, meaning if you have smaller values, you will have faster simulations. So again, because it is an iterative process, you can play with these values. So if you have a large complex situation, you are using smaller values for the domain dimension parameters, while you are using didn't want to close, while you are using larger values for the mesh creation, which would be these ones. So again, that was the advanced settings. That were the advanced settings. Let's change this. Okay, just to have a faster simulation, I will have a larger refinement factor. And let's run our simulation. Consteel always asks to save the model, because during the simulation will be created different elements or model objects, like load cases, layers, loads after generations. So we will change the model. Therefore, it is recommended to save the model before the simulation. And if it is saved, the simulation it just starts. So it begins with the pre-processing phase, then starts to extract the edges of the building, to introduce in the domain, which is containing the blocks. Then this refining mesh procedure starts, and when we have this mesh, the next step is the simulation, which again, in this simple, easy scenario, it is quite fast. So we have our simulation already run. We are doing the post-processing and sending the load case to Consteel. Here is a log where you can follow these steps. So, for example, if you have multiple cases, like in this scenario, we have 0 and 90 degrees just started, you can check in which direction, which step took how long, just to understand better how for your geometry a simulation is performing. So you have constant communications or constant informations in this log panel. And also, if we have any warning messages or error messages, which means we cannot go on with the simulation, we are communicating in this panel. So this is the logs, but the simulations were finished successfully. So in this scenario, we just ended the simulation part. So at the beginning, I said that we have 5 icons, just to repeat these. So we had these two have for the effect definition and surface definition. This is for the Eurocode. This was the simulation, the wind simulation procedure, or this is the dialog for that. And we have the wind load generation from simulation results, which we can also obtain from here. So when we have simulation results, these are saved on our computer. But what happens in the background? I will just quickly show you. So I have this FALCON default model. I have a lot of examples here. I have these FALCON simulation results, which is just a simple text where you can, it is obviously it is important for us, but you can check the parameters of the simulation, the results. So it is a text format. You don't have to bother with these, but these are the results. And you also have, for example, generation log. If you have any errors, you can send us these errors with what we are saving, or also if you have the simulation errors, but in this scenario we did not have. So we had this default model here, and we had here we have the result, and that's all. Okay, so this is our part. This is the FALCON part, let's say, or the Consteel part. But we also are saving the results of every simulation temporary according to OpenFOAM. So here you have both cases, so which we just performed for 0 and 90 degrees. These are again separate cases. You can open it, and if you install at the beginning ParaView, you can check, for example, the results directly by OpenFOAM. So here it is. Just quickly, I have this one, and here I can set to see my actual building. And just really quickly, it doesn't matter, you don't have to bother with these, but I just I thought that it is important to know that this is the actual simulation result, which we are using to project the results to our mesh. So again, this is a much complex mesh, and which can be distorted along the way. In this scenario, it is quite, so it is not, but again, you can, or you should check always, not always, if you are interested, you can check here. So fortunately, we have the simulation results, which we performed for the 0 and 90 direction, which I will be using for load generation. Here we have another dialog with several parameters. Again, if I have results, I have a green flag if everything is can be. So if I have a result, I can decide if the load evaluation is averaged or the maximum, because you probably seen that the meshes are a bit different, or the sizes of the edges. Here at the finite volume mesh, it is always at the edges is always more faces where results are calculated than in our mesh where we are projecting. This is because to capture always to capture higher value or higher section values at the edges, and you can decide if you are averaging or choosing the maximum value from those one. Also, if you are using the loads on zones generation type, it is also taken into consideration which value the average or the maximum is used for load creation. You can also set external pressure limits for suction and pressure, which, for example, for the Eurocode, you have at the E zone at the leeward side of the building, you have minus 0.5, say CPE, or the pressure coefficient value. So you can use these limits to implement these values in your loads. But now let's see how the first one is looking like, the uniform surface load on mesh element generation type. So if everything is okay, I have results in every mesh, which is obviously not too, it's way more sophisticated that we would like to see, because for every mesh, I have a specific load value. So for example, if I just hide the surface values, just to see only the loads, if I select a specific load, I have this factor here. For example, I have the windward side, and I have different values. Okay, and I have this for both of the directions for every mesh. This is when we project the values directly from our OpenFlow mesh. But what happens if I'm using a zoning methodology where another parameter occurs, or I can set, which is the number of wind zone categories. This is a value which defines how many intervals, according to my results, meaning that I have a max or a minimum suction value and a maximum pressure value. And in this range, I have, or I can have 8 different zones defined, which is by experience, the 8 is a value which can show or can reproduce something similar that happens in the Eurocode, meaning that you have, or you will have at least 3 zones in the side walls. You also have multiple zones on the roofs, but at the windward and the leeward side, you will have only probably 1 or 2 zones. But let's see how does it look like. So if I press again, in my load case, everything will be deleted and recreated accordingly. So for 0, this is how does it look like. And for 90 degree, I can turn on the values just to see, because previously we just generated the Eurocode values, which we can compare. But again, because these are load values, these can be used for structural analysis. So I will compare immediately when the actual finite element mesh will be created for the members, just to have nodal loads on every element, because it will show exactly the difference between the load values. But again, this was a scenario when I choose the load generation on zones type. We have another one, uniform surface loads on specific zones, which requires certain portions to be defined. This is a user, this is a possibility for the users to create specific portions of the model, which are where they would like to see certain zone numbers. For example, we have side walls from 0 direction and side walls for 90 direction. This is just a quick example. And I reload the generation dialog. And if I choose on a specific zones, I will have here the defined portions. I can set certain values for certain direction. So for example, for the side walls 0, I would like to only see 1 value at the 0 side, because it will be a windward, for example, and a value of 3 at the 90 degree. And accordingly for the other portion. So let's see what happens in this case. My load cases are regenerated again. And as I said, I will see only 1 at the leeward side and 3 on the 3 zones on the side walls for both cases. So therefore, I will have only those values which I would like to use, for example, for I have a certain wall where I would like to design the secondary elements, and I generate the loads accordingly for that wall only. So this is a simple tool. This is only a, let's say, it's a beta version of our tool, because it is just the simplest approach, but we have other ideas for automation purposes. Okay, let's go back for the zones scenario just to compare the result quickly. I recreate again the both directions, and if I have a load case defined, I can make sure that my yes and run a finite element just to see at first the few results. As nodal loads on my beam members. So for example, for a 90-degree, I have a 0.62 kilonewton for every finite element, which is similar for simulation. However, for suctions, the values are smaller, but the idea is that these are easily comparable. And in general, for windward side, the results are really appropriate to Eurocode values. And having this finite analysis or finite mesh with loads, I can run a static analysis for all of the load cases just to see some deformation, maybe to compare them. For example, for simulation 0, I have flexion of the structure. Probably for 90 direction is even more interesting. I have this 27 millimeters in this direction. Let's compare with the Eurocode. The Eurocode is a bit higher, like 20 or 25% at max. So I have values that I can compare. Again, we have reactions that we can check, or we should check maybe, because we can have a global reaction or the reactions of the structure. So again, these are loads that can be applied to the structure directly and can regenerate it, reevaluate it really easily. The simulations can be re-performed. So it is a really interactive tool. Okay, this was the live demo part, and I would like to open also some other modules, because I really prepared these two. I have, I think, this one, because previously I showed you this building where the secondary structure was designed. And I would like to just reopen that model again, just to see some results on this standard-ish building. And in the meantime, it is opening in my other screen. Just a second. Here it is. So I have the structure again. As I said, we have the secondary structure with a lot of elements. And from our point of view, is probably much more interesting. The zone loads on the structure from 3 specific directions. Because this is the X direction, this would be the 180-degree case, where, for example, we have this pressure where the height difference is in the building. We also can check, or can see really easily, that we have those. Actually, we have 4 zones instead of 3, because simulations at a certain building height, obviously, can capture this distribution, where obviously the higher part of the structure is much more, the suction values are much higher there. So there will be have an additional zone which is which have a higher external pressure coefficient value. But let's say these two here, for this example, for instance, it's quite fascinating that we have this minus 1.2 in average as a zone A. We also have this minus 0.9, or here minus 0.6 for the zone B. and we have minus 0.5 for the zone C. So again, we have these zones comparable, and this is really easy to use for 3 directions, but not only orthogonal directions, but for instance, we have this 245 direction. So again, we have every zone here with its own velocity pressure value according to its height, or the load transfer surface's height. We have external pressure coefficients, which we can compare. We have a load intensity. It is colored accordingly. So these will be the results for this case, for example. Another one, which is maybe a bit more common, a simple hole structure, just to check the results, because for this scenario, I would like to show you in 3 or comparing 3 different methods. The first one would be the Eurocode. This would be the simulation, which I will show you immediately in the model. And also for this scenario, I chose this one because this is a case for which we have a simulation result a wind tunnel test performed. Therefore, we have exact pressure or external pressure coefficient values that we can compare. So this is a good example, or we can compare how the simulation is in comparison with these results. So let's see the Eurocode first of all. This is again a typical only one zone windward load. We have these A, B, and C loads on the structure. We have an F zone, which is typically on the edge, or sorry, at the corner of the windward side, and so on. So this is a typical Eurocode. These are typical Eurocode values where we have this minus 1.2 value, we have minus 0.8 and minus 0.5 and 0.7 for windward. So let's remember these and how these look like from simulation. From the start, we can see that the actual value is 0.48 kilonewton per square meter, while from the simulation is 0.49. So it again, the windward side is quite similar. Let's see the suctions. For example, here we have a minus 0.9, while here only at the top we have this close to that minus 0.2 value, and the distribution is then quite similar. We have this minus 0.5 at the end of the structure. But let's compare the roof, which is not typically like at the Eurocode, because we don't have the F zone. Instead, we have even higher values at the middle. But this is not, it is not wrong, or it is not something like, so we don't have to consider immediately that it is a wrong value, because in reality, according to wind tunnel test, this is exactly the case, that at the middle, because for certain proportions, so for certain building dimensions, these F zones are not necessarily appearing. There are situations when these G zones are higher. And also an important thing to mention that we are considering as a point of view of the Eurocode, that it is a certain degree is from the 0 degree, for example, it is taking into consideration neighboring or zones like in total a 90-degree zone. So at the end of the day, it is not always the case that we get these F zones, but for example, from the wind tunnel testing, where we have these minus 1.4 at the very edges, we have this minus 1 value at the so-called G zone, and we have this distribution like this C-shaped, I don't know, this shape, which we can see also in the simulation, that we have these higher values in this region, and that minus 1.1 value for the external pressure is quite close to that range that is in the according to the wind tunnel test. So this is a simple scenario where we can also capture things like disturbances according to the mesh. I chose this scenario to show that this is a value that you can check that the width of the zone is exactly according to the Eurocode. So we have this, let's check it for 90 degrees, for example, that we have from this point to this point to until here, we have this 1 meter and like 9 centimeters, and also for the Eurocode, I have the similar width of the zone, which makes comparable. And this was because I accepted the recommended value according to the building dimensions, but I also have to take care of the proportions of the building, because in this scenario, for example, I only have 3 meshes here close to the wall, which leads that I have this triangular and I have this mesh disturbance, and it is not that fluent, for example, this mesh. But again, these are situations which you can iteratively resolve, and you have to see the bigger picture. What are the reactions of the structure? What are the deformations according to this? And the main zones, which would be the D zone, the windward side, and the sideward highest suction values, if are in accordance. And according to our findings or our experiences, this is really promising, because for this basic case, we started the validations and we really see the resemblance of the Eurocode. So again, this would be a simple building scenario. And this is a model which I choose to go on with this community development to show you how we imagine these steps or this whole beta testing process. So this would be the last part of my presentation. And as you already know, we are committed in the continuous development and reform of structural engineering, but we are aware of that the power of our community is required to achieve these goals. And the community that we have with a lot of dedicated engineers who are enjoying to pushing the limits, and we know because they are using Consteel, they really like the freedom, and they really like to see the real behavior of the structures. We really consider that it is a good community to try our ideas and to try to validate these post-processing steps to have this FALCON commercial version. So symbolically, I would like to offer this tool by registering in this community testing process. The model for this real-life sculpture actually was offered to test our tool by one of our dedicated customers from Romania, Gordias, who are also open-minded regarding simulation methods. So I would like to hand to you this tool to test by completing our form, our FALCON beta community testing registration form, which I will show you immediately where you can find. But first, just quickly go on through the testing process, because the first step would be the registration, which is not only so that we have the deadline is until the commercial version is published, because you can join anytime. We had today this FALCON plugin demonstration. we release the tool and the validation period will start. And we would like to organize a few online workshop sessions where will be open discussions regarding your experiences, how we are progressing with the validations, what we see, what are our recommendations using the tool. If you have any issues, we can consult, we can discuss together. But obviously, we also have our support platform, which in the meantime you can use anytime when you have a certain issue. At the end, we have a roundtable discussion, our last workshop session, which we will have, we'll organize together with our international Consteel meetup, which is generally, or usually it is in April or May, which also will be an open discussion where we will show probably the last version of, or the first commercial version of FALCON. And before we launch, we would also like to organize training, a day-long training, which is will highlight not only the usage or the functioning or the function of this tool, but also the theoretical background, the validations behind this, and every important aspects of using this tool. Regarding the validations, I would like to show you our part. What we are doing right now is actually that for the typical Eurocode building proportions or dimensions, we would like to take or to execute a parametric comparison or a parametric study where we will compare these values with Eurocode and also with wind tunnel tests. So this would be the validation part from our side to calibrate the tool. And like the example that I showed previously. And what we are expecting from you is to send test models, where you were using for standard-ish cases, where you defined the wind loads according to your engineering approach, near to or together with simulation results, which can offer a comparison of the tool, and we can see for real-life scenarios how our tool is performing, and we can calibrate and add even more functionalities. So obviously these were all these models will be won't be published anywhere, so these are only just models that we prefer to contain only loads. You don't have to share with us any structural, so analyzed models with beams, nothing, only loads on certain structures. So how you can obtain FALCON? First of all, you have to install. I will show you immediately where you can download, but first, just one thing to mention, that during the installation, you can always choose if you would like to install OpenFOAM, which is not required every time, only the first time, or when you consider that there is, or we will launch a version where OpenFOAM or inside OpenFOAM we make modifications, because generally FALCON will be developed, or it is developed separately. Therefore, when you install OpenFOAM, or when you download the full installation package, it is larger and it takes a bit more time. But when you are just using FALCON or installing later versions of FALCON, it will be really quick. So you only have to install once. And regarding the manual and support, I will show you in our website immediately. Just open those pages. Here we have. So you will have at the plugins, you can download FALCON. Regarding installations, you will have informations in our manual, our brand new Consteel 18 or manual which we launched together with Consteel 18, where you can search and really easily. It is a really interactive tool where we also where you can find manuals for axes or for desk grip. So all our documentation is here. So here you have the installation steps. You will have a quick theoretical background informations, also informations regarding the user interface. So I really recommend to check this manual before using the tool. And again, in the knowledge base, we will constantly update, or we constantly publish articles regarding validation or simulation topics. And at the end, I would like to close with this registration form, which you can find at our blog. So yeah, FALCON is coming soon. Here you can register to our community development phase, which, if you are involved in testing, it is obviously for this cooperation, we are also offering discounts. So we really think that this is a cool possibility to try. Also Consteel, for those who are not familiar with Consteel but interested in simulations, but in general, if you would like to Consteel or would like to try this new tool, we are really excited. Thank you again for your attention, and see you soon when we are testing together in our community. Thank you again. Bye.